So let's speak about the next speaker that will enlighten us on how we can optimize usage of LLMs via smart caching. I'd like to welcome on stage Mr. Stavros Vassos.
Hi. Mr. Vassos is the co-founder and the CEO of Helvia.ai, a startup that is transforming business operations with conversational AI since 2018, even before AI was cool. He has worked as a professor in the Sapienza University of Rome, where he taught master and PhD courses about AI and interaction design, and he did his master and PhD in AI in the University of Toronto in Canada. Stavro, it's great having you with us today.
Great. Hi, everybody. Thanks for being here on Saturday afternoon and just before lunch. I'll try not to keep you too much out of it. I'm Stavros. I'm one of the founders of Helvia. We have been working for a while on chatbots and AI assistants, and I'll start with some observations about how things are moving in this space, and then I'll tell you a little bit about how caching and different techniques can help make LLMs more efficient. So generative AI has changed a lot the way we think about AI assistants and now agents, and also how we build them, we design them, we monitor them. And there's, of course, amazing things about it, and there's also some challenges. And a couple of challenges, the way we like to think about them is, one, the generative AI hype challenge, that essentially it's easy to start and make a proof of concept very quickly to reach maybe the 60% of what you expect to, and then it becomes increasingly more difficult to actually make it to the highest, let's say, performance that you expect and make it in production and work in a robust and scalable way. And the second challenge is related to that in fact, to make this, let's say, not about GenAI in general, like let's focus on AI conversational, like chatbots, copilots, assistants, etc. And there's an underlying hard truth about making these systems work well, and that is that there is a kind of GenAI last mile challenge, that essentially to make something work well and in quality, the way you would expect it, it requires to configure and fine-tune, let's say, the lower level of AI components that are there. So essentially, from one side, you can buy things as solutions that are, let's say, they work out of the box, but they are limited. And on the other side, you can build custom solutions that take time and they're costly, as we know. And as a company, we try to fill in that gap. We have been developing a platform that is no-code and is able to reduce the complexity, but also help fix the things that need fixing and tune this balance between quality and cost. And this is related to the talk that I have today. So one main issue with the cost of AI assistants, one main component that makes them costly, is that every time you use an AI assistant, you're actually calling an LLM to do something. And sometimes you're calling it many times, not just one time. And just to have a motivating example, think of a customer support scenario, the typical thing, you have a chatbot or an assistant now with an LLM, and there's many conversations. There's like, in a medium volume even scenario, there's 5K conversations per day, and probably 4 messages on average per conversation. That's 2K of messages. And just observe that there's a lot of these, let's say, questions that come in that might be similar to one another. So there might be tens of questions about, I lost my password, I don't know how to do it, what should I do now, or how should I change my password, the typical stuff. And there are other ones that are not as common, like maybe if you're in a banking domain, I lost my card, what should I do now? And some others that are really particular and they don't overlap with another one. Like I have my whole scenario about what happened and I need some help. Okay, so as you know, the way LLMs work is that we feed them with some stuff and they feed out some information and we count these things with tokens, and most probably this scenario would have some RAG thing behind it. If you don't know what RAG is, don't worry, I'll say a little bit about that later. So with a conservative, again, case, these 20K messages, each one might incur more or less 2K tokens each one, and that gives us, just for one day, 40 million tokens, right? So these cost. Of course, you can say, yeah, but a year ago they were costing so much, now they cost 100 times less. It's not really a big issue. It might not be. If you have just one assistant for your company and it costs, I don't know, maybe $50 a day, it's fine. But there are many use cases that this is critical. For one, us as a vendor, for instance, we have dozens of these cases. So if you just multiply it by the 15 or 20 or 100, this becomes a big number. And even a 10% difference on that makes a big difference. And there's also other things that are related to that in fact, this 2K that I'm saying here is a very conservative number, and as we move into use cases that we want to use LLMs with more power and in more difficult scenarios, we may be calling them many times, or we may be calling them to think about themselves, like these newer models that do reasoning now, and that multiplies the type of tokens that we need to pay for. So the question that excuse me, I want to give you some ideas about and share some things that have been happening, and also some things that we did, is that can we make these tokens go down without sacrificing much of our precious accuracy? And the answer is yes, and we can see that with a combination of techniques, this can go down from 50% to 70%, and that makes a very big difference. And one thing that I'm going to say a little bit more is the idea of caching in the traditional sense. Like, let's cache some data that came in, and then later, when we need them, let's use those cached data instead of trying again the LLM to do that question for us. But that's not the only type of caching that is there, so I'll just give you some very high-level overview of two, at least, different types of caching that are around in the LLM space. One is probably more in the news lately, and it's called prompt caching. And the idea there is that we, on top you see there's two lines. One is about prompt caching, the other one is about response caching that I said before. And the different columns show how they fit in what they try to do and what we gain. So prompt caching is let's say, it's a system that when we use an LLM with long contexts and long instructions, think of it like you have a copilot and you have like hundreds of these instructions about what it should do, and then at the end you give some context more and you give a question. There's a big part, could be even 50%, that is repeated. So there's systems that they can cache this processing of the first part of the prompt or the system of the instructions, and the next time, if it's fast enough to the previous one, it just keeps them in memory and continues from there. This is something that is very interesting because you don't sacrifice anything. So if that happens to be the case, then the next call you have, you can gain all of it without, let's say, losing of accuracy or anything. It's a very smart mechanism of doing caching. And then the other type of caching that I said before, response caching, is kind of something that happens outside of the LLM system. So the first one, we don't control it. If you're using an LLM by OpenAI, they control it. The second one is response caching, and has to do with getting answers from the LLM, keeping them on the side, and then sometimes not even calling the LLM at all, because you can see that some of the answers you already have. And these things can be combined. Okay, I hope it made a little bit of sense. In any case, I'm going to focus now on the second part that's called response caching. I'll just flash a quick piece of information about prompt caching that you can find online. Essentially, as I said before, the part of caching the input to the LLM, right now for most of the providers you can find it, and it's controlled by them. It's not as, let's say, straightforward to see which is best, because there are different parameters there. Think of it as a way that they keep a little bit warm the LLM for you for a few seconds or minutes, and if the next call is very similar in instructions to the previous one, you may get some gain in costs and speed. While on the other side, the response caching I was referring to is essentially like something that we would think as a proxy that, where is that? Here it is. As a proxy that first will ask our own repository of things that we stored there as a cache. If that seems to have the answer for us, then we use it. Otherwise, we'll call the LLM, and then we save lots of money. And the tricks here are related to the let's say, the notion of having this caching system work in a semantic way, not just in the normal way. Like if somebody says, I lost my password, and then another one comes and says, I lost my password, then that's fine. If there is the stateless system and responses in the same way to all people, I can just use the previous response. But somebody might not say exactly the same thing. They might say, I don't know what is my password now, maybe I have lost it. So this one, in the normal caching way, doesn't fit exactly. You need to do something more than that. And that's why it's called semantic caching. And the goal of the next few minutes, 9 or so, is to show you some tricks that we have been working on that are interesting to make this semantic caching become even more effective. Okay, first of all, let's try to see how most of the cache approaches work now, the response caching approaches. The idea is that, as I said before, whenever we have an LLM and we ask a question and it comes back, that we store them. So what do we store? We store the queries. So think of all of these gray dots here as queries. We store them, and we also store the answer. We store the queries, we vectorize them through an embedding layer, some embedding model, and then when a new query comes, now with the embeddings, like let's think of this as a new query, this one in the middle. What we can do is we can say, is this semantically similar with any of the queries I have stored already? And if it is, then I can pick one and serve directly the answer that I served to the other query before. This is fine. It works well on average, but it's also prone to errors. And that is because if you've worked with embedding models, you know that this similarity is not really always robust in the type of things you do. It's very good in recall, as we say. So if you take the 10 closest queries, then many of them, and the closest ones will be there, but not necessarily the top one is going to be the most, let's say, semantically close to your use case. So what we have had as a thought to make this more, let's say, precise, was to say, okay, so we've seen these kind of things in many other techniques in AI. Why don't we do some kind of voting? Why don't we do some kind of agreement? So we started investigating how it would be if instead of just checking all the queries that are similar and picking one, we would somehow broaden the horizon and take into account many of them, not just one, the closest one, and have them agree on themselves if they have one suggested answer to suggest. And it seems that this works, and it has it gives better accuracy. There's a lot of details involved, but in any case, this is the first trick. So the first trick is, let's not just look into the closest neighbor, whatever that is, and if it's close enough, then serve an answer, but broaden the horizon, get a lot of queries that we've seen before, and try to figure out from this collection of them if they agree on something. The trick to make it mathematically, to test it, is to use a kind of entropy metric that essentially measures how, let's say, different and chaotic are things or how aligned they are. Okay, this is part of a work that we presented last year in EMNLP, a conference about NLP that is, a nice venue for this kind of works. And in the meantime, we started building tools to make us actually make use of these ideas in production, make it understand how it's best for us to use and optimize. And the first thing to do was to make a tool so that we can try these different approaches with different thresholds and different parameters. So, I mean, there's many systems you can go in and say, I want a cache, and I want this type of similarity, and then you run it. Okay, and then you wait, and maybe it works well, maybe not. So this is a tool that you can actually run instances of different types of parameters and types of caches that use agreement or not. And this is a plot that shows around 100 of these examples on an actual real data set that we have from a real use case. And now we can see there's actually a trade-off we can predict even. And what you can see here is two lines. One line, the blue line, is, higher and left is better overall. I'll tell you what that means. But the blue line are experiments using the caching with agreement, while the yellow line is experiments using caching with just checking the best closest match. And what happens here is you see on the horizontal line that as you go to the right, you call the LLM more, so you become more accurate. I mean, if you call the LLM all the time, then you're 100% accurate with respect to what the LLM would do. If you call it never, then the cache is not very good at it. So you need to find a balance about when should you use the caching and when not. And these are the different parameters to make it happen. And then maybe I can point out that with maybe sacrificing something like 5 or 4% up there of your accuracy. So this is the, this is the accuracy here, right? So you can get something like calling the LLM only 40% of the times, so essentially saving 60% of the calls. Right, but in order to make this work and really understand how this works in more complicated scenarios, I want to dive in a little bit into question answering. So you have an AI assistant, it's answering questions, you have an LLM to answer questions, and how that usually happens through Retrieval-Augmented Generation. How many of you know what RAG is? Okay, I was expecting a bit more. But anyway, the idea is this, that usually when you have tons of data, you don't just take all of them and put it in front of an LLM and say, now, please, answer to me. Instead of that, you do 2 steps. The first step is you somehow do a retrieval part. You filter the data. You get just a small part of it with the user query. Then you go and take the small part, not just all of the data, with the query, and then let the LLM respond. And the reason I had this here is to point out that usually when you take your data, you don't just put it as is. You do this thing that's called chunking. So you take the data and chop it in small pieces, very small one actually. Even each one is like a paragraph. And this is the point I want to make. Actually, let me go to this slide. That usually you take a PDF and you break it down to small paragraphs of 2 sentences or 3 sentences. And if you switch your mindset from doing that in this way into something that's more semantic, so there's something called semantic chunking now, and instead of that, just notice that maybe there's many paragraphs on the maybe top, the purple ones, there are many paragraphs, small ones, that they all refer to the same topic, like when do I get a bonus when I play a game online? There's 20 different ways. So if you put them all together, then this becomes the section about bonuses. And then there's another 15 small points that talk about what happens with your password. And if you put all of them in one somehow semantic chunk now, a bigger one, or a section, if you will, then this enables, then this would look like this. This enables us to do something that's very interesting. And that is what we call RAG with citation. So we do the same process as before, but now the data are these bigger sections. And the LLM, whenever it needs to choose how to answer, we can force it to choose just one of them, which will be good enough, doesn't need to combine small pieces, just one of them. And now with the answer, we get not only the answer, but actually the source, where it came from. Of course, you can do that with chunks as well, but now you get one robust section that everything comes from there. And the note here is that makes it very interesting is that in this way, it's almost like you're classifying every user message or every question based on the number of sections you have. That unlocks many possibilities, even though it might feel a little bit strange now. I'll just say that, and then I'll wrap up. And the second trick I want to share with you is that the normal operation is what we said before. So you have your data, they have these big sections, then you select some of them, then the LLM answers and gives you also the source. I picked that section there. And then what you can do is you can actually cache this information. You can cache this metadata. So you can say, now I know that this question came from this section. This question came from this section. And having all this in your cache, which is right here, then you can have on next questions to check the cache if you know where the question comes from. Okay? And the interesting part now is that if you actually have a cache hit and that you know for a particular query you need to answer it from this section, you have now already a much simpler problem. And that simpler problem can be solved with a much smaller and cost-effective model. So you can do a model switch and in this case, use an SLM, a small model instead of an LLM, and save cost and time and everything. Okay, a couple more things and I'm done. We need more tricks than that. These are just 2 tricks. And why is that? Is because that every new thing that comes in essentially makes us use more tokens. I'm going to skip that. And I'm going to say that we have been doing a lot of work in how we can make this question answering and RAG and assistants be more effective, be more interpretable. There's some things on our webpage on the labs section, and we're excited to see what other things are happening there. Maybe there are other things that happen in the lab, in your lab, that are not published. Feel free to reach out to us to talk. And thank you, everybody, for being here. And hopefully I didn't take too much time of your lunch. Thank you.
Stavros?
That was great.
Yeah, that was very inspiring. And I think it was a long-form response to one of our questions earlier about, how we can make usage of AI tools and LLMs more cost-effective. So thanks. We don't have time for questions now, but you will be around if
Sure.
anyone wants to
Yes.
to chat with you. Okay, thanks a lot again.
Thank
Thanks,
you very
everybody.
much.